times 10 to the power of h.
All right, all light travels at the same speed. The speed of light being 3.00 times 10 to the 8th meters per second, right? So if wavelength is measured in meters and frequency is in hertz, which is 1 over per second, or 1 over second, what is the formula for the speed of light? What's the formula for the speed of light?
Speed equals frequency times wavelength.
Frequency times wavelength equals the speed of light. Now, those two things allow us then, when we have the frequency, we can calculate the energy. But we can use those, that characteristic of light, that all light travels at the same speed, but with a different wavelength, to identify certain metals, and that's what, or certain elements, and that's what he was able to do. Once I can open this back up again. There's going to be a lot of silence on this one, apparently. Talk to my iPad every once in a while.
So much easier for me to lay back it's across your room from me. I feel like they outside you can't hear
Yeah.
What kind of light do they use? Like measure the speed of light? Like that kind of light, or?
I would have to read up to be exact. I believe what they, I mean, you can do it. You can measure the speed of light with a microwave and a chocolate bar. Yeah. Because remember, every type of light is different. Microwave is a form of light, radiation, right? So what we can do, that's not what I want. So what you can do is put a full-length chocolate bar in a microwave. And I'd have to double-check the time. I've got the experiment at home somewhere in one of my books. But you can put the chocolate bar, and if I would taught physics, I'd probably do it a little bit more to measure the speed of light. But you can put the chocolate bar in the microwave, and based on the where the melting occurs in the microwave, you can tell what the wavelength of your microwave is. I think so, yeah. Now, because light travels at different wavelengths, what we can do is get it to diffract. We can get that light to separate using a prism. All right? And what we're going to see here is a brief little video, and you'll be able to watch the whole thing at home with sound if you like, when you click on the PowerPoint, because the PowerPoint will be loaded separately. But what happens is, and we'll see this in class, we'll do something. A high voltage light, give out the light goes through the prism, and it separates. Because each light travels at a different wavelength, when it passes through a substance, it bends slightly differently, giving us a distinct pattern of different wavelengths, which we can use to identify that element if we compare it to knowns. All right? So we're not going to worry about that too much right now. Those of you who've already been doing your online work for the online neon discharge lab, that's what you're doing. We're going to do it in class with an actual neon discharge tube. You can hear the sound right there. Now, so this was the one he got for hydrogen, and that's what led him to his understanding that the electrons were in different energy levels, and then he could study which levels they were giving off as they were excited. This is just a quick explanation of light, a little bit more. You know the visible light spectrum, Roy G. Biv. That's visible light, that's our middle section. Red to blue being longest wavelength to shortest wavelength. But we don't always think of things like radio waves, microwaves, and ultraviolet and X-rays as being light, right? We probably think of ultraviolet a little bit because we talk about it with sunlight and burning our skin and cancer and things like that. But they're all forms of energy. They're all forms of light, just like visible light. Visible light is just what our rods and cones in our eyes can see. Now, radio waves are really, really long. How many of you have ever listened to AM radio, like you were going downtown for a Bears game or something, and you listen to pregame on the AM radio? What happens as you start driving through downtown? It gets fuzzy, especially at AM radio. You could be listening to AM radio clear because it's broadcasting down your road. As soon as you pull into a parking garage, AM radio goes out because the waves are too big to fit into the structure, right? This even happens if you're out on the highway going out to like Iowa. As you go under a bridge, the radio waves of AM will often fuzz out more than any other waves because they're longer. They can be as big as the buildings downtown. So we lose the connection that we had with them. All right? FM radio's a shorter wavelength, so we're able to get it better or hear it better downtown. Still can get interfered with all those big buildings in tight spaces, but it's better. But it doesn't travel as far as an AM radio wave because the AM radio wave doesn't get as much interference as it travels over the thing because it's hopping over lots of structures.
Is it like the same thing when you're listening to the radio and then you go to like the mall, like to park your car, and then just suddenly it's the same thing?
Yeah. All right. Now gamma rays, on the other hand, have very, very, very short wavelengths. But that translates into a greater what? Remember that formula. If the wavelength is really short, what has to be really big? Frequency. So they hit the same spot over and over really fast. Right? And that provides them with the ability to do more work or provide more energy to things. And that's what causes damage to your body. That's when we talk about radiation damage. It's because the wave is hitting something in your body and exciting it, causing it to mutate in some way, to change in some way.
So what gives off gamma rays?
What gives off gamma rays? Gamma rays will come out of the sun. Some radioactive substances give off gamma rays. We'll be looking at those kind of things a little bit more later. But X-rays especially, we know what we don't want to, like you have to wear the lead suit. That's to protect you from a mutagen, which is the X-ray itself, which can mutate your body. If you're pregnant, right, they don't want you to get a X-ray because it could damage the fetus, right? When you're developing, that's one of the worst times to have a mutation, right? Right now you have a mutation, it's only going to affect probably that nearby cell for most of the time, unless it's a cell that divides on a regular basis. So, we talked about it, low energy on the left, high energy on the right, and that's because of their frequency, low frequency, high frequency, and that has to do with their wavelength, long wavelength, short wavelength, that would be causing the change. Does that make sense? All right? Don't forget, it's nice to remember Roy G. Biv. It can help you out on red, orange, yellow, green, indigo, violet. That can help you out on the PSAE test, things like that, knowing that that's the longer wavelength to the shorter wavelength. But again, all this comes back to us being able to spread them out and see the different wavelengths. And you've actually experienced this if you've tried to grab something underwater while your head was above water and the thing was underwater. When you look into the water and you try and grab, you usually miss the first time. because what the wavelength your eyes are receiving and seeing are slightly bent under the water, so the object looks just up or down from where you're looking. All right, so if you've ever tried to go, oh, why did I miss that? I grabbed right where I thought it was. That's why, because where you thought it was wasn't really where it was, based on the light being bent. Now, this line spectrum allows us to identify different elements, and that's what we're going to do in class in a few days. But it also allows astronomers to identify elements in stars and distinguish types of stars. They can kind of tell stars' ages, right? Because in stars, what's powering the star is fusion, the combination of elements. Not the fission of elements, the separating of elements, like we produce nuclear power here on Earth, but fusion, which brings the elements together to form a new element. Hydrogen and hydrogen coming together to form helium. Right? Helium's forming together with hydrogen to form lithium. So forth and so on, right? Building blocks of matter. Well, so if you saw lots of iron in a star, would it be young or old? It's old, right? Because if you see that spectrum a lot, it's old because you can tell it's radiating energy from a giant substance, not a small, easily fusible substance like hydrogen, but a substance that has been fused multiple times, probably from different things within it, right? That's when stars start to fall apart as it goes along, and then they go through supernovas and things like that.
Where do the neutrons come from? It's a little bit too neutron.
They're there. Well, because remember, there's isotopes of helium. And those are less stable, so they're probably more likely to fuse. I'd have to research nuclear fusion on the sun and stuff, but I would believe that's probably why. Because the nucleuses of those, I believe, are theorized to be formed during the Big Bang, right, of all the hydrogen helium. But then they're fusing together as we go along. All right? And there's also some radioactive decay that could cause that as well. Now, oops, going too fast. Now, so Bohr's model, what he discovered on this, did some great things. It allowed us to explain the periodic law. Why are properties similar in each group? It told us the halogens are more reactive because they want to be like the noble gases. The alkali metals are also very reactive because they want to be like the noble gases. They want to gain or lose electrons to have that stable outer level, Araceli. Araceli. Come back to us. All right, does that make sense? All right. Now, the drawback to his theory. We talked about this the other day. It didn't explain the shapes or patterns of these orbitals. It wanted to say they were in circles, but that didn't seem to really work. It explained hydrogen, but it didn't explain the others. The math didn't work out on all the others. All right? Now, we did see that these energy levels were there, right? And that the lower energy fills before the high energy. The first energy level seemed to fill, then the second energy level, the third energy level, and it increased. But again, there was no in between. You were either at one level or at the next level, but you were not at halfway between. Right? Electrons could only be in one space or the other. And the further from the nucleus, it meant more energy. And that's where we come with the quantum model. All right? What the quantum model did was create basically a new term. The quantum. Or the quanta, which says this is the amount of energy to go from one level to the next level. You need a quanta, boom, you go up. Two quantas, you go up double. Right? And that's why you get the quantum leap.